So what do you think is easier? Do you think it's easier to express B as a combination of C? Probably, rather than C as a combination of B's. Yeah, that sounds about right. So let's express the basis vectors in B as linear combinations of the basis vectors in C. So that means we need 9 and 2 to be some kind of, let's go A1 times 2, 1 plus B1 times 3, 1. And we're going to need to do the same thing with 4 and 3. So are A1 and B1 easy to find? I mean, I could just take so this is 5. I'm going to get 15 and 5. And I need to drop a certain number of 2s. So to get to 9, I have to go to 13, 11, and 9. I have to drop 3 copies of 2, right? I have to drop 6. That should do the trick. So a little bit of work there, a little bit of thinking will get that job done. All right, so 15 minus 6 is 9, and 5 minus 3 is 2. So that should work with a little bit of trial and error. The next thing we need to do is 4, 3. And let's go A2, 2, 1, plus B2, 3, 1. So we know that 2a plus 3b is equal to 4, and we know that a plus b is equal to 3. All right. They're probably realistically going to be like, yo, let's look at this one. This is really just a is equal to 3 minus b. Yo, okay, cool. So now I can make a substitution, 3 minus b in for a. Boom. So we know that 6 minus 2b plus 3b is equal to 4. So that means that 6 plus b is equal to 4. B is equal to negative 2. I would not have guessed that b had to be negative here. And then if b is negative 2, we know that a is equal to 3 minus negative 2. So that a must be equal to 5. Okay, so let's just verify that. Let's make sure that we're okay with that. So if a is equal to 5, we have 10 and 5. And if b is equal to negative 2, we subtract 6 and we subtract 2. And that does get us to the 4 and 3 that we're looking for. Okay, so let's write that down. So here a2 is equal to 5. b2 is equal to negative 2. And then we can get rid of this. Now we have our coordinate vectors that we need, I think, in order to continue on this conversation. So 2 coordinate vectors, I believe, get stuffed into a matrix. So this is where I'm going to need a little bit of help. So let's arrange this as A1, B1. So negative 3 and 5. And then A2, which is 5, and B2, which is negative 2. So this matrix should do some kind of conversion for us. And I'm trying to remember if this is the matrix that goes from B to C or C to B. Now these are coordinate vectors with respect to the C basis. Right? Each column is a coordinate vector with respect to the C basis. So is this a conversion matrix that would get us from B to C? That would be my question. So let's call this A. And then we are gonna find the inverse of this because we do need this inverse as well. So negative 2, negative 3, and then multiply these by minus 1. And then we need to divide by the determinant as well. So 6 minus 25. What is that? 6 minus 25. That's where the 19 comes from. Okay. I am just going to get rid of the negative sign, and we're going to make all of these numbers positive. So one of these goes from B to C. One of these goes from C to B. And I know because these are inverses of each other, then when we multiply these, we should get the identity matrix. That's fine. But which is it, and could I figure it out? Now, I'm just going to do a little bit of thinking in green. So if I have one of these and one of these, we already know that this is 13 and 5. So the question is, how can I express 13.5 as the other basis, I guess, right? Can we easily figure out what we need, or what the coordinate vector is going to be inside the other basis? We could solve this. And see what happens. So 2 times 5 minus b plus 3b should be 15. This is 10 minus 2b plus 3b is 15. And this is 15 minus 10 is 5. So this gives me that b is equal to 5. If b is equal to 5, then a is equal to... I put 15 here instead of 13. No! Okay. B is equal to 3, I guess, then. So if b is equal to 3, then a is equal to 2. So the coordinate vector is 2, 3 in this particular case. The coordinate vector in this case is 1, 1. So basically we're checking to see if 1, 1, where does 1, 1 get sent to when we do a multiplication by one of these things. And if it gets sent to 2, 3, then we know the direction it's getting sent to. So if I do the multiplication by 1, 1, where does this go? This goes to negative 3 plus 5, and then 5 minus 2. So this gets sent to 2, 3, which is exactly the thing that I have down here. Now, I suspect that if we go 2, 3 here, and we try to do a multiplication, that should hopefully get sent to 1, 1, in which case I'm feeling pretty good. This is going to be 4 and... No, that's 15. Oh, my... Okay. Oh, phew. Okay. I was like, man, 19. Again, 10 and 9. That is also 19. That's getting sent to 1, 1. Okay, perfect. That's exactly the relationship that I wanted. So 1, 1, which is the representation of my vector in basis B, gets sent to the representation of my vector in basis C. So this first matrix is the matrix that starts at B and goes to C. Yes, I am happy with that. Can't believe OneNote wants me to write everything in monocolor. Okay, so matrix A is going to be the transition matrix from, what did we agree on? This is from B to C. Because if I input a coordinate vector in and multiply by that matrix on the right-hand side, it gives me an output that is a coordinate vector with regards to basis C. And we did the same thing down here, so we did the same thing and we found out that this matrix here, this A inverse, this is going to be our matrix from C to B, because if we input a coordinate vector with regards to basis C, my output is a coordinate vector with regards to basis B. Boom! There it is. Suck it.